from XSoPy, and today I'm going to talk about novel method for doing scaffold hopping free energy calculation. So I started this project when I was a PhD student in Stony Brook University, and I continued after I joined XSoPy. So um, so free energy calculation are becoming more and more popular in drug design industry, and we've seen a lot of workflow uh, for doing automatic setup of free energy calculation. And there are many publications showing that free energy calculations can have great impact in real drug discovery pipelines. And there are two major methods that's used in drug discovery projects, which are the absolute binding free energy calculation for the hit screening and the hit to lead stages, and the relative binding free energy calculation for the hit to lead and mostly the lead optimization stages. So and the reason um, uh, the absolute binding free energy calculation, the ABFE calculation, and can be applied at the earlier stages is because ABFE calculation can compare molecules with very different scaffolds, and RBFE calculation usually require the molecule to be studied have very similar scaffolds, and the only perturbation region should happen on the edge of the molecule. So, for example, in these pictures, this is an RBFE calculation. So we will have the benzene ring as the unperturbed region in the RBFE calculation, and then we'll only perturb the hydroxyl group into the hydrogen in this thermodynamic cycle. Um, Before we continue, I will introduce some theoretical background of free energy calculation. So I'm using the thermodynamic integration as an example here. So what we are trying to calculate in the thermodynamic integration is the right side of this equation. So we'll have to evaluate the coordinates under two different Hamiltonians. So one is for ligand A and the other is for ligand B. So we'll calculate the potential energy and take the difference and do the ensemble average and do the integration to have the free energy change from ligand A to ligand B. So one of the most important thing to have a successful TI calculation is we need to make sure the quantity in the bracket have a relatively small fluctuation. If the value in the bracket is going up and down like crazy, it will fail the TI calculation. So RBFE calculation is have commonly been applied to study the so-called R group perturbations. So what it means is just what I mean by R group perturbation is that the compounds we compare have the same scaffold, and the only difference is on the edge of the molecules. So we are not breaking bonds and making bonds in the RBFE calculation. So this kind of calculation has been very matured. So in my previous study at Stony Brook University, we applied the Amber TI to the blind prediction in the D3R challenge in 2018. And even this is a fully prospective ligand protein affinity binding prediction, we have a very good correlation to the experimental value. And we also have good results for retrospective protein mutation calculations as well. But at the year we participate in the D3R challenge, there is actually another set of molecules given by the organizer. that we can't compute because that set of molecules have different scaffolds which require scaffold hoppings uh, technologies in free energy calculation. And at that time, we still haven't figured out how to do that in MBTI. But scaffold hopping is a very important strategy used in medicinal chemistry to modify the property of compounds. So by doing scaffold hopping, we can change the rigidity of compounds to improve the binding affinity and also the drug likeness of the compound. And in some examples, we've seen that changing the rigidity can lower the toxicity by eliminating off-target binding. And also changing the scaffold will allow us to create new substitution sites and also patentable compounds with novel scaffolds. Um, so even though the scaffold hopping is very important in drug design, but unlike the R group perturbation, which is commonly benefiting from the high accuracy of free energy calculation, scaffold hopping transformation were once considered forbidden in RBFE calculation. The problem is that to do a scaffold hopping transformation in RBFE calculation, we have to do make new bonds or break bonds in the during the calculation, and this will cause some technical issues. So, for example, if we have to open up this ring on the left side here, we will have to break the bond between these two carbon atoms. So if we are breaking the bond going from lambda equals 0 to 1, so at lambda equal 1, we will have these two carbon atoms at far distance as the bond interaction will turn off here. And so if we are if we are using TI and we have to evaluate this difference as I shown before, so at lambda equal 1, we'll have if we evaluate the coordinates we get here, these coordinates under the Hamiltonians of ligand A, we will have a very high potential energy here. So this will cause many issues in the calculation. First is we will have crazy fluctuation in the number we get, and also we'll have steep TI curves, and also these large numbers leads to rounding errors in computers. And the using bar will also fail as there just breaking bond like this will have very poor phase space overlap, which I will show later. So yeah, there is an existing method uh, for handling scaffold hopping for energy calculation. So it use lambda dependent bond interaction form. So it's like the soft core potential for disappearing non-bounded interactions in RBFE calculation, and so it avoids singularity at far distance. But this functional form is not implemented in every software, and actually many software doesn't have this functional form implemented. So to use the existing method, it's you need to have the few software to do that. So it's not in every software. So and for a non-scientific reason, and some of you may know that a novel method which does not require a lambda-dependent bond interaction functional form is desired. So we've developed a novel method to handle the scaffold hopping without actually using without using lambda-dependent functional form. For example, when we are doing a ring opening transformation, we'll first apply restraint, dihedral restraint on the ring to hold the ring in the right shape, and then under the restraint we will break the bonds. After we break bonds, we will remove the restraint, and if there are any still any difference, then we will do regular RBFE calculation to fully convert the molecules. Applying and the releasing, the free energy of applying and then releasing these restraint will be calculated and counted in the total free energy change. So this is similar to the attach pole release method. Um, so if we check, look at the distance distribution plot, we can see that when we are breaking the bond between these carbon and the oxygen atoms to open up the ring, we can see that with the restraints, we can have very nice overlaps, distance overlaps for these 5 lambda values. But without restraints, the overlap will be significantly poorer at the last 2 lambda windows. So the restraint we use is dihedral restraint with K equals 10 kcal per mole. And we also applied the same dihedral restraints on microcycles. So microcycles is just larger very large rings. So we will have to apply many dihedrals restraints to hold the microcycles in the right shape. But we can see, still we can see here, even using the same strengths for the dihedral restraints, for the same 5 lambda windows, we are still getting the sufficient distance overlap under the restraint. But without restraint, we can see that the last 2 windows, which is 0.99 and the exact one, almost have no overlap. So this is definitely will fail the TI calculation and the bar calculation. And also we come up with an idea for doing contraction. So it's good for ring and the linker contractions. So for contraction, the concept is that we will remove the non-bonded interaction for the contracted atoms first. Then we will break the bond need to break and form the bond need to form. And at the same time, we will add bond angle restraints to hold the contracted part in the exact center of the newly formed bond. And if there are any hydrogen in the contracted part, we will the angle restraint will have everything in the right geometry to maximize the phase space overlap. So this actually all the bond dihedral angle restraint we use is actually all have the regular functional form of molecular mechanics. So that means this method can be applied in any software without changing the code. So to apply that, for example, to apply that in Ember, we just modify the parameters of bonded interaction in the Ember PALM7 file. And then we throw this PALM7 file into PMEMD, turn on the TI, and the free energy of applying and the releasing of this auxiliary restraint will be accounted as contribution from bonded terms and will be reflected in the DVD lambda values of the PMEMD output file. And I guess this is similar for other software as well. So we've tested this method using test case studied by the existing method. Yes, sorry. Yeah, yeah, the animation didn't show up. So we've applied these 2 study molecules involving ring opening, ring contraction, and the linker contractions. One thing to note is that linker contractions is our method is the first one to show that we can do linker contraction in RBFE calculation. And all these calculations showed a very good correlation with the experimental values. And we also test our method in the for the microcycles. So microcycles, in my opinion, is more difficult to handle than the previous test case. So we have studied microcyclization and the change of ring size, and also addition of subrings on the primary rings. So also we get a very satisfactory, very good correlation with the experimental value. This indicates that our method is highly applicable to different systems. And we also applied these two protein mutations. So protein mutations will involve breaking up the ring of the protein and change it to a linear side chain. So we've studied 4 mutations in different proteins, and also get a good correlation with experiments. So in summary, we've shown that the method we have here, the so-called auxiliary restraint method, provide another good solution for handling scaffold hopping RBFE calculation. And the method does not require change of code, and it can be applied using standard Ember. And we've tested the applicability of this method using microcycles and protein mutations. And the test case was large enough to show that the method is reliable. So XTOPI has actually been using MBTI for a long time in almost every project. So this MBTI is helping us a lot, and is one of the most favorable and trusted tools among our medicinal chemists. And for those systems that's validated using retrospective calculations, usually finding compounds with high binding affinity is not a problem. And we are very grateful that Ember provide such a tool to calculate binding free energy with a reasonable price. And very frequently we are requested by clients to do free energy calculation using Ember TI. So with that, I would like to thank my colleagues at XTOPI for helping me with the research, and also my former lab mates, and Professor Dan Roddy and the Professor Carlos Semmelin for supporting me when I was a PhD student there. And also I want to thank Tyson for help with the Ember code. So with that, I will take any questions.